The following content has been provided by RWTH Aachen University.
So state charts are the next kind of representation you want to take a look at. They are also an improvement over STNs. They also deal with concurrency better than STNs. They are a little more practical than Petri nets, probably, because Petri nets are wonderful and clean as a notation, but that sometimes makes them hard to actually understand and actually get understand what's going on, especially if you have a mix of sequential and parallel things going on. Not with the simple dialog that we just talked about. It's very obvious what's going on, very clean modeling. The state charts are trying to take the idea of STNs, basically leave it as it is, but add a few things so we can deal with parallelism and other issues when they appear. They were introduced by Harel and are used, among other things, in the unified modeling language. So you might well have come across them already in software engineering, for example. As an example here, we'll be looking at a TV control panel, and this is a very simple TV. And I'll use that example to show you what the state charts do over STNs. The first thing that state charts allow you to do is to add hierarchy. That's a very simple thing. It doesn't really increase the expressiveness of it, but it means that we can basically take a state chart, put it in a box, and then refer to that box as a whole and have arrows going in and out of that box. We see this here at work. There are two, there's this big box here that is built around this subnet, basically, of the state chart. When you do this, you also have the option of creating concurrency. So in this case, on the left-hand side and right-hand side of this dotted line, we have two state charts, and these are being executed concurrently in a state chart. So that means that I can actually model two things happening in parallel by putting the state charts for them, which are basically state transition networks with these additions, putting them next to each other, putting the dotted line in between, and then looking at how each of them is or modeling the parallel aspect that I want to model. There's also the option of, when you do that, of referring to the, when you do an arrow, you can have an arrow going inside the state chart, which will mean that when you come from that state and you have this action happening, you end up exactly at that point. Or you can have an arrow pointing to the grouped parallel state chart here as a whole, which in that case raises the question, where does the subchart start? What does it do? Because we're no longer going from one state to the next. So in this particular case here, it means start at the last position you were at when you were last active. So these subcharts can remember, if you like, where they were, and then basically continue from there the next time they are being activated. So this arrow here, when you're in the standby state of the TV and you press on, will activate these two sub-state networks. Similarly, we have an option of creating a universal, you could call it escape. Remember the problem we talked about in the graphics tool, when we said, well, if I want to press escape to get out of every single sort of step in the drawing routine, I need to add a little arrow from every single state, label it escape, and say that will get me back to the main menu. That's very tedious. So this is the function that you get by putting a box around these things and then just drawing an arrow from that box. That means any state I'm in here, if this action happens, I will move to this new state. So I will leave the box and get up there. And then finally, we may not always want to start at the same state when we enter a substate network. We may want to remember where we were at last time. So it's kind of like a freeze drying of a subnetwork. On the left-hand side here, we have a subnetwork that has a little black marker. This is basically like the double circle you know from finite state machines in your algorithm classes. That basically marks the start state. So anytime this network gets activated, it will simply always enter this state. Even if it comes in through the box here, which basically just says, run the two state charts left and right. This right one here, when the on state is activated, the first time it will also start here because it has the start marker here. But this H, means that this is a history preserving start marker. So the next time this thing gets activated through the on button, it will remember where it was and continue from there. So this is the link, sort of, the history marker that you can put on a start marker and say, I want this thing to preserve its state between activations. This is all maybe a little weird. Let's play through this with the TV we're looking at here. This is a very simple remote. It basically has an on-off button, a mute button, and a channel button. So what we're looking at here is a remote that kind of looks like this. It has an on button. It has an off button. And then it has a reset button, which is probably going to be, on the back of the remote, and you can only poke it with a, ball pen or something. And then it has a mute button. And it has an SEL, it's a channel selection button. This is really for channel surfers. You cannot actually enter a particular channel. You can just press select to go to the next channel. So very, very simple, right? So that's our remote we're looking at here. And so what happens here? Or what are we modeling? Well, this TV is normally in the standby state, which is a fancy way of saying it's off. So the standby state, when we're in that state, we can press the on button. When we press the on button, we enter that compound state at the bottom, the big box. Entering the compound state means literally we activate all the state transition networks inside. We currently have two of them inside. They are parallel because they have a dotted line in between. So the left one gets activated and the right one gets activated. Where do they get activated? Well, that depends because we're not pointing to a particular state inside each of them. We're just pointing to the compound state, to the big box. So the local or the subnets will decide themselves where they will start. The left-hand one on the sound side will actually start in the on state, no matter where it was the last time when the TV was turned on. Why could that be a good idea? Why is that? That's a design decision that we just described, actually. Why could that be a good idea? Yeah?
Because the normal use case of a TV is to watch it and hear it.
Mm-hmm.
And maybe if the user forgot to put on the sound when he turns off his TV because he was telephoning or something, then the next time he puts on the TV, he will want the sound to be on and not to be off.
Right, that's exactly what's going on. In fact, I would go one step further. I'd probably say every time nobody will ever unmute their TV before they turn it off just to reset it into like a normal state. That sounds completely ridiculous. Like if I muted my TV and the next thing I want is it to be off, I'll just press the off button, right? And I won't worry about resetting the mute. So it makes sense not to remember that mute was active. While that's going on, I can also, and that makes perfect sense because that's how the remote works, I can also work my way through the channels. Now I said the only way to work my way through the channels is pressing the select button to go to the next channel. If I'm on channel 1, I end up on, and press select, I end up on channel 2. That seems to make sense. Then I end up on 3 and on 4. And here we can see that we modeled so that the thing should turn around and go back to channel 1 once you press select again on channel 4. Again, makes perfect sense, right? Since there's no way to go back one channel, I got to circle through. And notice how we're modeling these effects of the interface and the behavior of the interface here very precisely in the state chart. Now, where does the TV start when I turn it on the first time? Yeah?
First time on the first channel, but afterwards it will be on this channel, you just turn it off.
Exactly. So in the case of the channel setting, I want to remember where it was the last time I turned it off, because that's, again, pretty likely that you want to watch the same channel again. So that's why this has the little H marker here that says I'll start on channel 1 for the first time when the TV gets turned on the very first time, but after that, I actually want to remember which channel the user was on when he last turned it off. And then I'll go back to the same state. So I will maybe start on channel 3 the next time, because that was the one that was active when it was turned off. OK, so that clears up what happens with the on button, with the mute button, with the select button. We're left with the off button. That's also clear what happens. Anywhere where I am, no matter whether our sound is on or off and channels are away, of course I always want the off button to work, right? That's clear. So again, with this state chart, we're modeling that explicitly by making this drawing saying, no matter where we are in this, always make sure that the off button immediately turns the thing off. Clear. We're left with the reset button. The reset button is interesting because it behaves differently from turning the TV on normally. What does it do? Yeah?
It turns the TV on and sets the sound on and the channel on channel 1.
Mm-hmm. So the difference here to normally turning it on is that it makes sure that we end up here and here, right? So especially, this wouldn't really have been necessary because this substate network always starts in the on state anyway. But here we show a direct arrow into the box, not to the corner or to the edge of it, and saying when we enter this compound state through the reset arc, we want to go to this state particular. So we're overriding the history function and making sure that when the user presses reset, the TV resets itself to channel 1. Yes?
In this scenario, is it possible to press reset even though TV is already on? Or does the TV have to be off?
What do you think? According to the state chart.
It has to be off, according to this, but I
yes.
think the normal functionality would be to being able to press reset all the time.
Aha.
That's just why I'm wondering.
OK, no, that's perfect. Makes perfect sense. And that's exactly the kind of discussion you want to have in your design team based on a state chart like this, right? Because then it's crystal clear what you're talking about. You can say, well, right now, as you can all see, we've defined it to only work in the off state. Do we also want it to work in the on state? And you can have a discussion, and yeah, you're probably right. You want the reset button to also work in the on state, and then you can redraw your state transition network, your state chart to reflect that change. Right? So you're right. It probably makes more sense. And the point here is not to design the best possible remote, but just to show you that by making a state chart of an interaction like this, you can actually be very clear and very specific and unmistakable about what the system should be doing interactively. Okay. So this hopefully shows that this is a fairly useful notation to do this. Yes?
To redesign it in the way that you just said, would you just make an arrow from the big box back to the big box and then to on and channel 1?
Yep. Because anywhere you are in the substate of the compound state, anywhere you are, you always want the reset button to work. And it would leave the compound state, and the arc would then go back in the way the reset arc goes back now. Yes. Yeah, good. So we solved that too. Good. So that's the way to use state charts to make precise descriptions of how these things work. The important things to remember are that state charts will give you this option of getting a little parallel, getting a little concurrency into your system with this dotted line and several substates in one go. And that's the sort of the big power that you add to your notation over your traditional state transition network.
This content was provided by RWTH Aachen University.